All right, so if you're wondering what's going on in this picture here, you've got this pensive looking person who has a prosthetic leg. And this prosthetic leg, I mean, if you're going to have one, that's the one to have. That thing is like it's artful, it's pretty, right? You could wear this out on the town. It's like a dress up prosthetic leg. It's your Sunday best. Anyway, so it is substituted for her actual leg. Maybe she lost this leg in a motorboating accident, something like that. Maybe she was born that way. And it refers to the fact that in order to do the integration of a composite function, we're going to do it by a substitution of variables, right? We're going to take out our original leg and we're going to put this beautiful prosthetic limb in its place. Okay, so before we start that process, let's look at a differential equation. We have dy dx, this is in Leibniz notation, dy dx is equal to f of x, and we're going to rewrite it in what is called differential form. What you do is you separate your dy dx's as if this is some sort of fraction. You're going to take this dx and you're going to bring it over here to the other side. And essentially that step is called a separation of variables. You're putting the y's over here on the left and you're putting the x's over here on the right, and you're going to integrate both sides. So let's talk about what each of these little pieces mean. So first up, you have your dy, the differential of y. And if you take a look at the picture here, here's your differential of y, and what it's doing. This is your pink line here is your tangent line, and the blue curve, of course, is your original function. And what do we use this tangent line for? Well, we use it for lots of things, one of which is to approximate your function here, someplace around your point of tangency, which is this point P here. So in this case, the differential of y is approximating your delta y, and your delta y is your actual change in y in the original blue function that's right there. Next up, we have our dx, which is our differential of x. And look here in the picture, your differential fx is the same thing as your delta x. So think in terms of a slope where you have your dy over your dx, or your delta y over your delta x. In this case, those two things are exactly the same. All right, so once again, this dy is the amount of vertical change in your tangent line, this pink line that's right here, whenever your x changes by dx, right? And the original delta y is the amount of change in your original function, the blue one here, whenever x changes by delta x. It's like your slope. Okay, so to solve this differential equation, you're just going to integrate both sides. You're going to take the antiderivative of both sides, and you denote that, of course, with that stretched out looking S symbol. So it looks like this. So what's left out here is the fact that what you would do is you would put the integral sign on both of these sides. And on the left-hand side, when you take the antiderivative of dy, it's as if this is a 1 dy. Antiderivative of that would just be a y. And I'm taking it with respect to y, that's why I have a y here instead of an x. Right? And then you can read this thing as the antiderivative of f with respect to x, or you can reread it as the indefinite integral of f with respect to x. And of course, this is going to simplify to some sort of antiderivative, and then don't forget your little plus c here, okay? All right, so now with a composite function, we're going to basically work that chain rule backwards here. So think of this thing being the product of some sort of chain rule. And what was the original chain rule? Well, it must have been some antiderivative of this f that's here with respect to this g of x function, and then plus c. And we're going to accomplish this task of taking the antiderivative of something that came from the chain rule with a substitution. It's too hard to see when it's like this, but when you do the substitution, I promise you, it's going to be a lot easier. So here is the general antidifferentiation rule of composite functions. We're going to let g of x, that's this interior function here, be a function whose range is an interval I. We want to talk about the range because remember, the range, that's the output of g of x, becomes the input of the exterior function, the f of x. And let f be a function that is continuous on I, right? So whatever the output for g of x is, that range becomes the input, and f of x must be continuous on that interval, right? In order for us to be able to apply things like the fundamental theorem of calculus and stuff, okay? And g is differentiable on its domain. It has to be in order to be part of the integrand that's right here. And big F is supposed to be an antiderivative of f on this interval I. And then you can see that we're basically just working the chain rule backwards, where this capital F here is the antiderivative of f. And once again, we're going to accomplish this with the substitution rule. So pay attention. This is what the substitution rule looks like. Okay, so we're not doing an actual example. We're going to look at the substitution rule, and then we'll apply it to an example here right after this. Okay. So what we're going to do is we let the interior function equal your favorite substitution variable, which of course is a u. You can use whatever you want, but use the most common one. And then you take its derivative. Why are we taking its derivative? Because it's the interior function, and the chain rule has the derivative of the interior function attached to the n. Okay, so we have a du dx is equal to the g prime of x. And then I want to separate those variables. We want to rewrite that thing in differential form. Of course, you can skip a step here and go straight from u is equal to g of x straight to your du is equal to g prime of x dx, right? You can separate the variables as you take the derivative. Okay, so here is what I want to take the antiderivative of. I can see that it came from some sort of composite function, right? Came from the chain rule. And then I'm going to take this g of x function that is inside here, and I'm going to replace it with u. And this is what it's going to look like. It's just the antiderivative of f of u. All right, but I've got some more, right? I have this g prime of x dx. I'm going to take this out, and I'm going to replace it with, boop, you guessed it, the du that's right here. And so it's going to look like the antiderivative of f of u du. And now whenever you see this function right here is really easy to integrate. I can just apply one of those very straightforward antidifferentiation rules, right? So the antiderivative of this should be big F of u plus c. And then of course you want to rewrite your function in terms of its original variables, not in terms of the u, but you want to take that u out and replace it with the g of x, okay? So let's see this in an actual example here, all right, all typed out. So here is our function that we want to find the antiderivative of. We've got the antiderivative, or the indefinite integral, of 2x times the square root of 1 plus x squared with respect to x. Now, the first thing that I want to notice, like when I'm doing this on my own, I want to be able to notice that I need to do substitution on this. And how do I know? I know that because I can see that there's a composite function going on here, right? There's more than just a single part that I can't just, I can see that there is a product, and there is no such thing as a product rule here for antidifferentiation for us, right? So it must be, this must have come from some complicated rule like the chain rule, right? Okay, so what's the part that I'm going to use for my u? What is the interior part here? It looks like it's going to be this 1 plus x squared. We're going to let that equal our u. What do you do next? Well, if it's chain rule, I have to have the derivative as part of the integrand, so I'm going to take the derivative of this with respect to x and then separate the variables. Or like I said, you could just do that in one step, save yourself a little bit of time. Now it's time to rewrite this. Now notice that our du is equal to 2x dx, and you have that in the integrand. Here's your 2x and here's your dx. Here, to make it super plain, I'm going to separate these two things. So you can see the square root of the 1 plus x squared, that's your u that's right here. So we're going to replace that thing with a u. Boop. And this is your du, and you can see it very plainly here, the 2x and the dx is going to become your du. And so here's your integral, right? It's the antiderivative of the square root of u du. Don't worry about that it's a u instead of an x. Hey, you just integrate it with respect to u. But of course, before you do that, you probably want to rewrite this to the 1/2 power, and then use the power rule on this, which would be, let's see, u to the 3/2 divided by 3/2, which is the same thing as 2/3 when you multiply it, and then your plus c. Is there anything left to do? Yes, there is. You can't leave your answer here in terms of u because the original function was not in terms of u, it was in terms of x. So you're going to take your u out and replace it with 1 plus x squared, and here's your final answer. Okay, so you can see here that your answer is in, your final answer is in terms of the original variable x, or whatever it turns out to be. And well, just like with any anti-differentiation, you always know if you're right. And the way that you know that you're right is by just taking the derivative of what you got, right? So check your answer by taking the derivative. Let's go ahead and do that real quick before we wrap up this video here. I'm going to take the derivative of, let's say that this is my function, f of x is equal to 2/3 1 plus x squared 3/2 plus c. And, I would have a particular number there instead of this c. And then let's find its derivative. And I have to use the chain rule to find its derivative because I have a composite function here. And I'm going to leapfrog this power down. And when I do, I have 2/3, the original 2/3. That's going to be multiplied times the 3/2, the new power, times 1 plus x squared. Subtract 1 from that exponent. It's going to be to the 1/2 power. And then since it is a composite function, I've got to multiply it times the derivative of the interior, which is this 2x. And then we can see our cancellation crayon, of course, changed to blue this time. That's weird. All right, so these things cancel out. Nothing else cancels out. However, we can rewrite our answer. Mike at Luck Brady, f prime of x is equal to, let's bring this 2x out front, and then change this into radical notation as the square root of 1 plus x squared. And that should look familiar because that is our original integral right there.